Hello, dear colleagues. We would like to present our project, which is a solution to the answer correctness prediction problem. So the problem is to predict whether students are able to answer the next questions correctly. Note that the problem has two aspects which allow us to achieve different types of valuable results. Firstly, we can solve the predictive task, and it will allow us to increase the efficiency of the learning process. For example, if we know whether a student, based on his or her previous learning experience, is able to solve a particular task at a given moment of time, then the tasks can be given at a proper pace and complexity. Secondly, we can solve the explanatory task, and it will allow us to find features which significantly affect learning process, and that is a widely discussed topic in many sciences. Let us now proceed with the EDA. So to perform EDA, we took a subset of the trained data of a reasonable size, namely 1 million observations. We decided to take the metadata into account. However, it was unclear how to connect lectures to the questions, because part and text variables are different for them. Thus, we added only the questions metadata to the training sample, which resulted in the addition of the following new features. Among these newly added features, correct answer and tags will be considered later. ID ones can be one-hot encoded, but the part feature requires further consideration. So the part feature shows which part of the exam the question was taken from. It is natural to ask whether different parts are characterized by different correctness levels. And indeed, we see that some parts are more likely to be answered incorrectly compared to others. And these are the last part of the listening section and the first part of the reading section. This makes this variable informative for model building. Okay, let us proceed to the original variables, and for the time being, let us consider these three ones. So the prior question had explanation feature is a binary one. So to understand whether it is informative, we computed the association coefficient, which shows a weak but positive connection of the feature to the target variable, and thus this feature is informative. We have two numeric features, timestamp and prior question elapsed time. As the histograms show, the timestamp one is rather noisy and reflects both states of the target variable. To deal with this problem, we created a timeInt variable, which shows the time period between two consecutive questions. We see that the longer the time period is, the higher the fraction of correct answers is, probably because of the longer time for consideration. However, this logic seems to be wrong for longer periods of time. For example, there are several observations with almost a half a year gap between them. To account for this, we add a binary feature isGap based on our heuristic. As for the prior questions elapsed time variable, we observe that for the larger values of the feature, it is more likely that the user's answer is correct. This dependence is not trivial, however, and needs to be taken carefully, because there are questions which were answered in less than 0.3 seconds, whereas the maximum answer time was 5 minutes. Considering the description of the variable, it implies that the variable probably depends on the number of questions in the bundle, and we include the corresponding features for the current and previous bundles. Finally, we have noticed a peculiar thing, that according to the data description, these features must be nonce for the first bundle of each user. However, it's not always the case. And we have corrected this issue. And now let us proceed to the data preprocessing procedures.
So, based on that, our preprocessing is as follows. First of all, we find and replace glitch values. Then we treat all the non-values as special and either encode them as a separate category or impute them with some large impossible value. Then we add information about the topic of each question via features part and text, which we one-hot encode. And then we add all the new features that we've already described. Next, we drop some rows that represent lectures, as we found that their occurrence in the dataset is pretty rare, but keeping them would require much more sophisticated model. And finally, we also drop features that are meaningless or already preprocessed in some way. The dataset has the panel structure, and so it would be logical to one-hot encode different ID features, but there are too many of them to encode, so we drop some of these features and the other we leave as is. We also added a feature experience that helps to account to the bundle structure, as it represents a number of answered questions of a user at a given timestamp. In the end, we came up that it's better to stick to tree-based models, as they are not so sensitive to unencoded categorical features and outliers. And specific models that we've chosen are gradient boosting and random forest. For gradient boosting, we used XGBoost classifier. At first, we used a small chunk of a dataset to quickly test some hyperparameters and select those that perform best as just constants. And so we chose values for subsample, learning rate, and max depth. Then we used cross-validation, and we grid searched through parameter call sample by tree and regularization parameters. We found that L2 regularization with lambda 0.5 is always better than any L1 regularization. Finally, we did a clean train on a larger dataset, and the final result of area under ROG curve is 0.71. We can see that most important features for XGBoost are related to questions categories, but we also see that previous explanation and number of previous questions are also important.
We have also decided to compare the results of the gradient boosting with the random forest classifier, and we defined the grid search with cross-validation on a max depth and number of estimators domains. And we have found that the best estimators hyperparameters are 15 for the max depth and 20 for a number of estimators. We also have checked if the fixed effects can be dropped, so that we have omitted the user ID individual effects and obtained the decrease in the modal quality. Then we omitted the bundle ID and question ID, which gave almost no impact in comparison to the previous case. Also, we have experimented with the shuffle option in the train test split and discovered that the shuffling gives a higher ROC-AUG score, which evaluates the modal's performance of the classification problem. The shuffling makes a more realistic approach if we assume the question's order to be random, not depending on an increase in hardness. Then every question is new for each person, and we can shuffle the sample under the split. The random forest classifier with the highest quality scores has defined these features to be the most important ones. The result seems to be logical that the time of solving the problem, the experience of the user, as well as the explanation of the previous question and the indicator for the hardest question part have a significant weight in predicting the outcome. So, we can proceed on to the comparison of the modal's performance. Both modals agree that part 5, seeing the explanation of the previous question and the number of questions in the current bundle, are important in predicting the answer correctness. The gradient boosting has a higher ROC-AUG value, which implies that the model's higher predictive power. The random forest performs worse in terms of prediction, but the feature important table contributes to the explanatory power of the results. Controlling the individual fixed effects amongst the users, questions, and bundle results in a higher quality, since these features catch the heterogeneity between the corresponding groups and use it to predict the outcome. Overall, one might conclude that both trained models perform much better than a random 50% guess for the predictive classification problem, with gradient boosting working more efficiently. This estimator manages to extract patterns from tags and parts, some of which are not obvious at the first sight. And therefore, by being able to process a considerable amount of data regarding both observations and complex features, as well as to address the highly indigenous problem of learning abilities, the use of ML techniques helps to first enhance the prediction of the answer correctness, and second, implicate the features to give recommendation on developing more efficient teaching and learning strategies. Well, this brings us to the end of our presentation. Thank you very much for your attention. If you have any questions, do not hesitate to ask. Thank you.